I want you to just picture something in your mind's eye for a second.
Oh, I love a good thought experiment.
Right. So imagine you're standing in the pitch black of the Atacama Desert in Chile.
Oh, wow. Yeah, one of the driest, most remote places on Earth.
Exactly. High altitude, totally isolated. You look up at this perfectly clear night sky, and you're expecting quiet, still stars. But instead, you see this massive, intense burst of pure energy.
It's quite the visual.
It really is. It's four distinct, blindingly bright, pure yellow lasers, just shooting simultaneously from a single point on the ground, piercing straight up into the dark, starry void.
Honestly, it looks exactly like a defensive planetary shield from some sci-fi blockbuster.
Yes. Your brain immediately goes to like a space battle, like we're firing into the cosmos to intercept an incoming threat.
When you see those four beams cutting through the darkness, I mean, it genuinely looks like we are weaponizing a mountaintop.
It totally does. But the wild thing is, this isn't science fiction. Those beams are completely real. So welcome to today's deep dive, everyone.
Thrilled to be here with you all.
We are exploring some absolutely phenomenal insights stemming from the European Southern Observatory, or the ESO. This was detailed recently in a May 17, 2026 article by Adrian. And our mission today for this deep dive is to pull back the curtain on these four massive sci-fi lasers.
And spoiler alert, they aren't intercepting alien ships.
Sadly, no. No alien space battles today.
Mm-hmm.
But they are actually some of the most advanced scientific tools ever constructed. They are completely revolutionizing our ability to map and, actually understand the universe. So, okay, let's unpack this.
Yeah, let's get into it. Welcome, everyone. It's a real pleasure to dive into this with you, because looking at the mechanics of what the ESO is doing here, it becomes super clear that sometimes the most awe-inspiring futuristic technology we can build, well, it isn't designed to travel to other dimensions or blow things up.
Right.
It is engineered simply to strip away the distortions of our own world, just so we can get a clear look at what's already out there.
Which is so poetic, honestly. But to understand what these massive yellow lasers are actually doing, we have to establish the physical barrier they're designed to defeat.
The invisible wall, so to speak.
Exactly. We have to talk about the atmosphere, and specifically the mechanics of atmospheric turbulence.
Yeah, what's fascinating here is that the very layer of gases protecting our planet, like the thermal blanket that regulates our climate and blocks cosmic radiation, it is an absolute nightmare for optics.
A total nightmare,
Yeah.
because it's not just empty air, right?
Right. When we look up, we are looking through roughly 100 kilometers of swirling dynamic fluid.
Which is crazy to think about. It's fluid.
It is. You have different layers of air at completely different temperatures, and they're all moving at different speeds.
And because cold air and warm air have different densities, they actually have slightly different refractive indices.
Precisely. Light travels at slightly different speeds depending on the temperature and density of the air it's passing through. So imagine a photon of light, right? Emitted by a star millions of years ago.
Just cruising through space.
Exactly. It travels across the absolute pristine vacuum of deep space in a perfectly straight line for eons. It is completely undisturbed.
Until it gets here.
Yes. In the final fraction of a millisecond before it hits a telescope mirror on Earth, it slams into our atmosphere. It gets knocked around by a high-altitude jet stream, then passes through a pocket of freezing air, then a turbulent updraft of warmer air radiating off the ground.
The light wave just gets totally shredded.
Totally shredded.
I was actually thinking about the best way to visualize this mechanical distortion. And it's like, imagine you're trying to read a text message on your smartphone.
Okay.
But the phone is sitting at the bottom of a moving, rippling swimming pool.
Oh, that's a great way to put it.
Right. People are splashing, the wind is blowing the surface.
Yeah.
You look down, and you can see the bright glow of the screen. You know it's a phone, but the text is dancing. The letters stretch, they compress, they shift side to side because the moving water is constantly bending the path of the light before it reaches your eyes. You basically can't read a single word.
That is exactly it. And the astronomical term for that phenomenon is seeing.
Seeing. Just quote-unquote seeing.
Yeah. So when astronomers talk about poor seeing conditions, they mean the atmospheric swimming pool is particularly turbulent that night.
Ah, I see.
For decades, the limit of ground-based astronomy was dictated entirely by this effect. I mean, you could build a massive, flawless glass mirror to gather as much faint light as possible.
Right, spending millions of dollars on this perfect mirror.
Exactly. But the resulting image would still be a blurry, smeared-out blob, because the atmosphere scrambled the data before the telescope could even record it.
Which presents just a massive engineering hurdle, because, you can't just drain the atmosphere like you drain a pool.
You kind of need it to breathe.
Yeah, breathing is fairly important, so you have to figure out a way to literally unbend the light. And that brings us to the actual solution for the ASO, the four bright yellow lasers,
The sci-fi lasers.
sci-fi lasers. How do you fix a chaotic, constantly moving layer of gas miles above your head? Well, you hack the sky.
You project your own reference points. Because the core issue with looking at a distant, distorted star is that you don't actually know what it originally looked like.
Right, you have nothing to compare it to.
Exactly. You don't have a clean baseline to measure the distortion against. So the astronomers at the ESO bypass this by using those incredibly powerful lasers to create their own glowing points of light high up in the atmosphere.
Which is just wild.
It is. It's what we call artificial guide stars.
But they aren't just like shining a super bright flashlight onto a cloud,
Yes.
right? The physics of where these artificial stars are created is honestly brilliant.
It relies on a very specific quirk of our upper atmosphere. So at about 90 kilometers up in the mesosphere, there is this very thin layer of naturally occurring sodium atoms.
Wait, sodium, like salt.
Well, sort of. These atoms are actually the microscopic remnants of meteorites that burned up upon entering the atmosphere.
Oh my gosh.
Right. And the lasers we see in those striking images, they are tuned to one exact specific frequency, 589 nanometers.
Because that's the magic number for sodium.
Exactly. This is the precise wavelength required to excite those sodium atoms. When the laser hits that layer in the mesosphere, the sodium atoms absorb the energy and they glow fiercely.
That is so cool. We're essentially using lasers to make meteor dust glow.
Pretty much.
Just creating four distinct artificial stars 90 kilometers above the telescope.
Yeah.
And because we created them, we know their exact mathematical parameters.
Right. The computers know these glowing points of light should look perfectly round and perfectly sharp.
Okay, so then what happens?
From there, the system measures the degradation. The light from those glowing sodium atoms has to travel back down through that same 90 kilometers of turbulent, swirling atmosphere that is ruining the starlight.
The rippling swimming pool.
Right back through the pool. So by the time the artificial star's light hits the telescope sensors, it is warped and distorted. But since the computer algorithms know exactly what the artificial star should look like, they can analyze the blurry incoming image and instantly calculate the precise mathematical shape of the atmospheric distortion.
At that exact microsecond.
The algorithm can determine that a pocket of cold air just bent the incoming light wave by a fraction of a micron in a specific direction.
And once the computer knows the mathematical shape of the atmospheric distortion, it can counter it.
Exactly.
And this whole process is called adaptive optics. But I have to admit, this is where I get a little lost in the mechanics.
It is incredibly complex.
Because the atmosphere is moving at hundreds of miles an hour up there. You got wind, thermals, pressure changes. It's highly chaotic. For a telescope to correct that, it has to physically alter the shape of its mirrors based on those algorithm calculations.
That's right.
How can a massive piece of heavy, solid glass possibly bend and shift fast enough to keep up with the wind? Like, that sounds physically impossible.
Well, if it were a traditional, rigid telescope mirror, it would be impossible. You can't bend a giant slab of glass that fast. The ingenuity of adaptive optics lies in what are called deformable mirrors.
Deformable mirrors. Okay.
Yeah. We aren't talking about the primary massive mirror that gathers the light at the very front of the telescope. Deep inside the optical train of the telescope, the light bounces off a specialized secondary mirror.
Oh, I see.
And this mirror is incredibly thin. I mean, sometimes just a couple of millimeters thick. It's essentially a flexible membrane of highly reflective glass.
So it's pliable.
Extremely pliable. And mounted directly behind this thin sheet of glass is a densely packed grid of hundreds, sometimes thousands, of microscopic actuators.
It's like little tiny pistons.
Basically, yeah. These are often piezoelectric or magnetic pistons that can physically push and pull on the back of the glass membrane. So the supercomputers analyzing the distorted laser light calculate the exact inverse of the atmospheric turbulence.
Wow.
Then they send electrical signals to those thousands of actuators, which warp the thin glass mirror into the exact opposite shape of the atmosphere's distortion.
Wait, the atmosphere is constantly shifting? The computers have to be calculating this instantaneously? It's basically acting like a pair of high-end, noise-canceling headphones, But instead of canceling out background audio, it's canceling out atmospheric light distortion.
That is a phenomenal analogy. I love that.
Because it's the exact same principle.
Right, it
Yeah.
really is. Noise-canceling headphones use microphones to measure the waveform of ambient sound, and then speakers generate an exact inverted sound wave to flatten the air pressure and create silence. Adaptive optics uses the laser guide stars to measure the waveform of ambient light distortion, and uses actuators to generate an exact inverted physical mirror shape to flatten the light wave and create a perfectly sharp image.
And the speed of this is what truly blows my mind.
It's staggering.
The algorithms and those physical microscopic pistons, they're adjusting the shape of that mirror hundreds or even over 1,000 times every single second.
Yeah, up to 1,000 hertz.
Just a relentless, continuous process of measuring the error, computing the matrix math, and physically warping glass faster than the blink of an eye.
It requires some of the most intense, low-latency computational processing power on Earth. You are mathematically freezing a chaotic fluid dynamic system in real time.
Which just sounds like magic.
It kind of is. I mean, without it, the imagery is just a smeared blur. But with it, ground-based observatories can achieve a level of optical sharpness that rivals or even exceeds what you would get if you placed that exact same telescope in the absolute vacuum of space.
See, here's where it gets really interesting, though. Knowing how this noise-canceling light technology works is honestly only half the equation.
True.
We need to look at what machine is actually firing these lasers and where it is pointing them. Because the hardware doing this at the ESO isn't just one standalone telescope.
No, it's much bigger than that.
It's an array called the VLTI, or the Very Large Telescope Interferometer.
The inclusion of the word interferometer is crucial here. It represents an entirely different layer of physics being applied to this problem.
Yeah, because the VLTI is actually a network of 4 separate, massive telescopes situated on the same mountaintop.
Yeah.
And they don't just, take 4 separate pictures and stitch them together in Photoshop later.
Right, that would just be a wide panorama.
Exactly. The system intricately combines the actual light gathered from all 4 telescopes to create a single virtual instrument.
And combining light from separate sources is wildly complex. It is not like pouring 4 buckets of water into one central tub.
Which is how my brain wants to picture it.
It's a natural assumption. But light travels as an electromagnetic wave. To combine the light from 4 telescopes, you have to align the incoming waves perfectly so that the crests of the waves match up with the crests and the troughs match up with the troughs.
Okay, crests to crests, troughs to troughs.
Exactly. This creates constructive interference where the waves actually amplify each other.
But the telescopes are spaced pretty far apart on the mountain. So because of the angle of whatever star they're looking at, the light wave hits telescope number 1 a tiny fraction of a nanosecond before it hits telescope number 2.
And that is exactly the problem. If you just bounce all the light into a central room, the waves will be out of phase. The crest of one wave will hit the trough of another, and they will completely cancel each other out. That's destructive interference.
Which defeats the whole purpose.
Completely. So to solve this, the VLTI directs the light from the 4 telescopes down into these subterranean tunnels using a system called delay lines.
I read about this. It's so cool.
It's amazing. These are mirrors mounted on motorized carts that are moving along precise tracks underground. They constantly adjust their position to artificially lengthen the travel distance of the light coming from the closer telescopes.
So they are essentially holding the light back, just delaying it by fractions of a millimeter so that all 4 beams arrive at the central combiner at the exact same physical phase.
Yes, down to a precision of incredibly tiny fractions of a wavelength of light.
Unbelievable.
It is an absolute engineering masterpiece. And by combining the light in this way, the VLTI acts as a single virtual telescope with a mirror diameter equal to the physical distance between the separate telescopes.
Oh, wow.
So you end up with a virtual mirror that is up to 130 meters wide.
And building a single solid glass mirror, 130 meters wide, is just impossible on Earth. It would warp under its own massive weight. It would take decades just to cool the glass and polish it.
Not to mention, no mechanism could possibly steer a piece of glass that heavy.
Right. So if we connect this to the bigger picture, you see the true power of this facility. The VLTI utilizes the 4 laser guide star facility we've been discussing. So you have interferometry, creating an impossibly large virtual mirror to gather incredibly faint light working in perfect tandem with adaptive optics.
Using those mesospheric lasers and supercomputers to cancel out the atmosphere.
It's just brilliant. You conquer the faintness of deep space, and you conquer the blur of our sky. simultaneously.
Which allows astronomers to look at some of the most difficult targets in the cosmos.
Like the one in the ESO data we're looking at today. The system was pointed at the Tarantula Nebula, which honestly sounds like a deep space horror movie.
It really does. But it is actually one of the most vital regions of space for astronomers to study.
Tell us about it. Where is it?
So the Tarantula Nebula is located in the Large Magellanic Cloud, which is a satellite galaxy orbiting our own Milky Way. It's roughly 160,000 light years from Earth.
That's a long way away.
Very far. But its distance isn't even the only challenge. It is an immensely dense, chaotic, star-forming region. It's just packed with massive clouds of ionized gas, interstellar dust, and brilliant, highly energetic young stars.
So if you point a standard ground-based telescope at a stellar nursery like that, what happens?
Well, the atmospheric turbulence completely smears the light of the young stars into the glow of the surrounding gas.
It just blends together.
Exactly. You just get a glowing, featureless cloud. You lose all the dynamic structure. But with the adaptive optics engaged, actively filtering out the atmosphere in real time, the haze just vanishes.
Wow.
Astronomers can suddenly resolve the individual protostars forming within the dust filaments. They can observe the intricate physical processes of stellar winds interacting with the gas clouds, which shapes the evolution of the galaxy.
These are processes that dictate how stars are born, which would be entirely invisible to us from the ground otherwise.
Entirely invisible.
So what does this all mean? I have to ask the practical question here. We are talking about subterranean delay line carts, lasers exciting sodium atoms 90 kilometers up, and supercomputers reshaping glass thousands of times a second just to fight the atmosphere.
It's a lot of work.
It is. So why go through all this effort on Earth? Why not just put the telescope in space, above the atmosphere entirely? No lasers required, perfectly clear seeing all the time.
It's the logical alternative, right? And space telescopes like Hubble or James Webb have obviously transformed our understanding of the universe.
Oh, completely.
But space-based astronomy has crippling logistical bottlenecks. First and foremost is the cost. Space telescopes run into the billions, sometimes tens of billions of dollars.
Yeah, that budget is no joke. And they take decades to design, test, and finally launch.
And you are severely limited by the payload fairing of a rocket. You can only launch a mirror so big before it simply won't fit inside the rocket, which is why James Webb had to be folded up like complex origami just to get off the launch pad.
I remember that. Everyone was terrified it wouldn't unfold properly.
Exactly. And furthermore, once a telescope is out there, it is essentially isolated. If a sensor degrades, or if a totally revolutionary new camera technology is invented 5 years later, you can't just drive up and install it.
Right. The hardware is frozen in whatever decade it was designed.
Exactly. But if we master adaptive optics, the entire paradigm shifts. We can build observatories like the upcoming extremely large telescope with primary mirrors nearly 40 meters across.
40 meters.
Huge structures that could never be launched into space. And we can build them for a fraction of the cost. If a new, faster supercomputer is developed for the adaptive optics, a technician just unplugs a server rack on a mountain and plugs in a new one.
Oh, that makes so much sense.
It drastically democratizes observational astronomy. It provides exponentially more observing time to scientists globally, accelerating our mapping of the universe without relying solely on a handful of multi-billion-dollar space assets.
I love that. By hacking the sky, we basically turn the Earth itself into the ultimate, easily upgradable space telescope. That is a massive paradigm shift.
It really is.
So just to recap the journey we've been on today, we started with this striking cinematic image of 4 massive yellow lasers slicing into the desert night. We uncovered that those lasers are carefully tuned to excite sodium atoms in the upper atmosphere, creating these glowing artificial guide stars.
From meteor dust.
From meteor dust, which is still my favorite fact. We explored how adaptive optics uses those stars to calculate atmospheric turbulence, physically warping thin glass mirrors thousands of times a second to unblur the sky.
Right.
We broke down how the VLTI uses interferometry to align light waves, creating a massive virtual mirror, and how this combined technology allowed us to pierce 160,000 light years into the chaotic stellar nurseries of the Tarantula Nebula. It is profoundly impressive.
Truly.
It's a reminder of human ingenuity, really, that when faced with the fundamental limitation of our own planet, our response was to mathematically cancel out the chaos of the sky.
It is a total triumph of physics and computation. And, reflecting on how flawlessly these real-time systems operate, this raises an important question, something I've been considering as we synthesize this data today.
Oh, do tell.
Well, we just spent this deep dive exploring how we use real-time algorithms to instantly calculate and correct the wildly unpredictable, chaotic distortion of 100 kilometers of Earth's atmosphere, all just to see a sharp image.
Yeah.
If our engineering has reached a point where we have the low latency computing power to achieve real-time distortion correction on something as vast as the sky,
Yeah.
imagine what happens when this fundamental technology scales down to the chaotic environments of everyday human life.
Oh, that's a super interesting leap. Where are you going with this?
Think about the applications. What if these same adaptive algorithms scale to our digital infrastructure, instantly measuring data degradation across chaotic global networks and generating inverse signals to ensure perfectly uncorrupted data transfer?
So like zero packet loss, ever.
Exactly. Or consider everyday physical optics. Imagine a pair of smart glasses or the windshield of a car equipped with a scaled-down version of this real-time optical correction.
Wait, like a windshield that fixes the view for you?
Right. Using algorithms to instantly measure the chaotic optical distortion of pouring rain, dense fog, or the blinding glare of oncoming headlights, and physically unblurring your vision of the road in front of you.
That is wild.
If we can algorithmically unblur the universe, what else in your daily life that is currently distorted, chaotic, or full of noise is about to come into perfectly sharp focus?
Wow. That is an incredible thought to leave off on. The technology to unblur reality is literally already here. It just happens to be sitting on a mountain in Chile right now. So for everyone listening, the next time you look up at a twinkling star, remember the lasers and the math working relentlessly to hold that light still. Thank you so much for joining us on this deep dive. Stay curious, keep looking up, and we'll catch you next time.